Okay. Hi, everyone. Thanks for joining in. So today we're lucky to have David Stutz. He's a research scientist at Google DeepMind, had completed his PhD at the Max Planck Institute for Informatics, has received numerous awards, including outstanding paper awards and dissertation awards, um, and really looking forward to the talk today. So thank you for taking the time to present today.
Yeah, thanks for having me. Thanks for the flattering introduction. Just again, if my kind of sound is bad or anything, just let me know. And I think because this is kind of this panelist Zoom setup, I'll try to monitor the Q&A a bit. If there kind of are any problems in between or people have questions and can't follow. Otherwise, feel free to interrupt me for those that can. Okay. So yeah, I'm here today to talk about conformal prediction on the ambiguous ground truth. And just to give you a bit of context, so for the last 1 or 2 years, we've been very interested in tackling classification tasks in security critical applications, for example, in health. And we're particularly interested in kind of reasoning about kind of uncertainty and handling uncertainty properly in these settings, because especially if there are high stakes applications, this usually turns out to be very important, especially in health. And we found that there are quite a few obstacles. So for example, classes in health usually have a very rich structure. There's kind of a very long-tailed class distribution. We have very rare classes. Some classes might be higher risk than others, and so on. But in this talk, I particularly want to focus on this last point, which basically says that in many settings, the ground truth that we usually kind of evaluate and calibrate and train with might actually be unknown to a large extent, or at least be uncertain. And the core reason for this, as illustrated here on the right, is that we gather this ground truth from annotators. So in health, for example, we ask doctors. And very commonly, especially on very ambiguous tasks and very ambiguous examples, these annotators tend to disagree. And this, of course, injects uncertainty into everything we do with these ground truth labels. And the talk today will kind of focus on how we can deal with this during calibration, specifically using conformal prediction methods. So this is a short outline. So the first block will be just a brief introduction on conformal prediction. So I remember I had a talk here before. So for some of you, this might be a refresher. For others, this kind of might be new. And then the second longer block will be on Monte Carlo conformal prediction, which is our approach basically to handle uncertain ground truth in very ambiguous settings using conformal prediction. Okay, so in conformal prediction, the setup, just to introduce some notation, is as follows. We have a model, which I already know pi, and this has usually some parameters theta, which are not that important. And we assume that this classifier somehow approximates our true posterior distribution of labels y given inputs x, right? So we have kind of a softmax classifier, for example. And then the goal is to construct confidence sets C. These confidence sets are subsets of our label space. In this case, we have capital K classes. And the goal with these confidence sets is to provide a so-called coverage guarantee. And this coverage guarantee can be stated as follows. We want the probability of the true label Y to be included in a confidence set C that we construct for the test example X to be lower bounded by 1 minus alpha. And importantly here, alpha is kind of a user-specified parameter that's independent of the problem and independent of the model. So you basically tell me what kind of coverage you want to have, and conformal prediction, or I kind of calibrate the model in a way that kind of guarantees this coverage. Because this coverage is guaranteed, the performance is usually reflected in the so-called inefficiency. Inefficiency is just kind of the average confidence set size. You can imagine if I have a very poor model, then I need on average to include more classes in these confidence sets to guarantee kind of a very high coverage. And the nice thing about conformal prediction, I think I already said it, it's independent of the model and data distribution. And it has very light assumptions, mainly exchangeability. Exchangeability of calibration and test examples. And exchangeability, for now, I think is just like a lighter version of IID, but we'll get into more details later. And on the bottom are a couple of examples, just to give you an impression of how this could look on CIFAR 10. So for example, on very easy examples on the left, these confidence sets might only include one label and it might be the true label, but on more more difficult examples, for example, the third one, we might actually include more classes in these confidence sets, and sometimes, depending on our alpha, the true class might not be included. Okay, so far for the setup, and in this talk I'll concentrate on a variant of conformal prediction called split conformal prediction, which I feel is very popular nowadays and is in practice actually very easy to implement and apply. And here we have essentially two stages. First, we define what we do at test time, and then we define what we do at calibration time. And the key thing at test time is how do we define these confidence sets, right? So given our classifier outputs, how do we construct the confidence sets? And here we just do this by thresholding so-called conformity scores E. In the simplest case, these conformity scores could be your classifier logits or your classifier softmax, and we threshold them by tau, right? So you can imagine, depending on my tau, I might include more or less classes. So this is fairly easy. This is a kind of a one-liner in NumPy. The interesting part, of course, comes into play when we talk about calibration. So at calibration time, we expect that we have a held-out calibration set that we haven't seen during training. And here we have capital N calibration examples. And on these calibration examples, we want to define our threshold tau. And the easiest way to do this is actually to define tau as a quantile. This is roughly, so for large N on the left, you can see this is roughly an alpha quantile. And we compute this alpha quantile over the true conformity scores. So we assume that on the calibration set, we observe the ground truth labels. So we know what the true conformity scores E for my calibration example xi with the true label yi are, and we compute the alpha quantile of those. And this is kind of illustrated on the bottom a bit. And you can think by this quantile definition, on the calibration set, we have by construction coverage 1 minus alpha, right? Because if we compute the alpha quantile, then 1 minus alpha cases, in 1 minus alpha cases of your calibration examples, the true conformity score is above the chosen threshold. And then statistics essentially tells us that as long as the distribution between calibration examples and test examples stays the same, we can expect the same guarantee at test time as well. Okay, so this is usually the easier formulation of conformal prediction. I mean, it's very easy to implement. Even calibration is usually just like 1 or 2 lines in Python. However, for this talk, I also want to introduce an alternative view on conformal prediction, which is more like a hypothesis testing view that will become important later. And here we imagine that for a given test example X, what we actually want to do is we want to test a hypothesis. And the null hypothesis will be that label K is the true label of our test example, right? So I can write this down. I call this hypothesis HK, and it basically just states that the true label Y is equal to K. So now, in order to test this hypothesis, I want to compute a p-value, which I can later threshold. And it actually turns out that these p-values can be computed very easily. They are often referred to as conformal p-values by simply looking at my conformity score of the test example for label K and just counting how many of my true conformity scores of the calibration examples are lower or equal to that, right? So you can imagine you have kind of a histogram of your conformity scores on the calibration set, and you just compute essentially the cumulative distribution to some extent of your test conformity score. You have this kind of correction factor +1 here, and then you divide by n+1. And it can be shown that these p-values are indeed uniformly distributed. So these are valid p-values, which means that in the third step, because these are valid p-values, I can just threshold them at alpha, right? So if K is indeed a true label, and my threshold is at alpha, because the p-value is uniformly distributed, I will have coverage at least 1 minus alpha. And for all the other classes that are not the true classes, they might be included sometimes, sometimes not, depending on the conformity score and the calibration scores. Okay, so just to give you an impression, maybe I should notice, of course, like both formulations are entirely equivalent. This is just an exercise. You can sit down and show this. If you want to save the time, have a look at our appendix of the paper I'll present later. And you can see how to do this, but you can implement it and it's exactly the same results. Okay, so here's an illustration of how this turns out on CIFAR 10. We have 2 different confidence levels in the rows, 5% and 1%, meaning we want to guarantee 95 or 99% coverage. And we are working with a kind of base model that has an accuracy of 82%, right? So there's a significant gap between the 82% that the model provides in a top 1 accuracy sense and the 99 or 95% coverage we want to have. So naturally, on average, we need to include more than one class in the constructed confidence set. So what these numbers are is essentially the average confidence set size, the inefficiency. You can see the higher the coverage guarantee we want to have, the more classes we need to include on average. And just as an illustration, the columns just correspond to different conformity scores E. Right, so on the left, these are just it's just the softmax output, but then APS and regularized APS are popular ones from the literature. Just to illustrate that there's of course a lot of work on choosing these conformity scores, but the procedures always stay the same. Okay, and just as a short reminder for those that were there last time, so in my last talk, we talked about conformal training, which essentially tackles a small misalignment between the calibration part and the training part, because we usually train with the cross entropy loss for optimizing top one accuracy. However, we calibrate usually for coverage and inefficiency, so there is a bit of misalignment. And in conformal training, we bridge that by basically taking this kind of split conformal prediction idea into account during training, so we can directly compute losses on the confidence sets rather than the model output. And this is actually very flexible in terms of the losses that we can optimize, and it's independent of the conformal predictor and that we use at test time, and because of that also preserves coverage. So if you weren't there last time, feel free to check out the paper. Okay, now to the main part of the talk. So this is about Monte Carlo conformal prediction, and here I'll walk you through basically 2 or 3 basic questions, and I'll actually spend quite some time trying to convince you, or hopefully convincing you, of the main problem that we try to tackle, which is that in many, especially safety critical applications, the ground truth that we use for calibration, of course, we also use it for training and evaluation, but here we focus on the conformal calibration bit, is actually uncertain. And the main reason for this is that the ground truth always comes from annotations. We always, in ML, most data sets, we don't have access to the underlying ground truth. So in a health application, we rarely have access to the actual condition, because this would require very invasive tests. But we usually have access to a diagnosis, for example, and these are essentially doctor annotations. And these annotators might disagree. On easy examples, not so much. On difficult examples, way more. And this induces uncertainty in the ground truth. And then the third part is essentially realizing that this is a problem. How can we handle this in conformal prediction? And this essentially leads to what we call Monte Carlo conformal prediction. Okay, so let's start with the first question. Where do our calibration labels, our calibration ground truth actually come from? So just to remind you, during calibration, why do we need labels? We need labels to compute these conformity scores corresponding to the true labels, right? So I kind of sample my or I assume that my calibration examples are sampled from my data distribution. For each example xi, I observe the true label yi, and I want to use these for calibration. Now, in practice, even on CIFAR 10, the reality is, of course, that this yi that we assume we have access to is, of course, never really observed, right? Because no one here was ever part of the data collection in CIFAR 10. Right, so if I would have been there and taken the photo and resized it to this kind of 32 by 32 image, then maybe I would know what the actual ground truth is. But in practice, as ML practitioners, we are less involved in the data pipeline, and so usually we have to trust what people tell us the label is. So what we kind of converged to in the last 10, 15, 20 years is basically a reverse process, right? So we have these observations and we ask experts for their opinions what the ground truth label should be, right? So of course you think that CIFAR 10 is actually fairly easy, but it turns out even on CIFAR 10 you can find examples where these annotators disagree quite a bit. So in this case, my initial guess would have been bird, but you see that most of the annotators actually say it's a cat. And so what we usually do is we say, okay, if we ask enough annotators and we majority vote the annotations, then this is kind of the label that we can work with, right? So in this case, the majority voted label would be cat. The problem of this, of course, you might already imagine, is that this ignores a lot of very rich information, namely that quite a few of the annotators say it could be a bird or even a dog, so there is uncertainty. Okay, So now this is basically summarizing what I just told you, but just to formalize it a bit more, what we want to have is labels from our data generating distribution P, but what we actually get on most data set is labels from a slightly different distribution, the distribution that I will call P vote, which kind of integrates this majority voting scheme, right? You can imagine that if we had access to infinitely many annotators and the distribution would look similar as here, we could argue that the true posterior distribution of labels given the input might look something like that. Whereas we, in practice, usually work with a one-hot distribution, right? So this step from kind of the original distribution to the voting distribution is, in this case, ignoring the ambiguity and going to kind of a one-hot distribution. So now, I hope that I don't need to convince you of that, but in this particular example, obviously, the one-hot distribution of the voted label and the true label might not be the same. There might be quite a significant discrepancy here. The problem is that in conformal calibration, in conformal prediction, we kind of assume that the labels we have come from the original distribution. So we need these distributions to be the same in order to get any meaningful guarantee, right? If we want to guarantee coverage with respect to the original distribution, we need labels from the original distributions. We only have labels from the voting distribution. So we need these two distributions to be the same. So now this might be a bit abstract, so let me try to convince you with two examples, a very simple toy example and then a more serious real example later. So let's assume we have these three classes. These are just three Gaussian distributions that I sampled. Of course, I made the problem a bit harder by creating some overlap between two of these classes, right, the red and the blue class. In reality, you can imagine that we actually observe, or there are actually additional dimensions, and in these additional dimensions, these classes might be perfectly separable. Right? But in practice, due to limited observational information, we only observe the first two dimensions where these classes are clearly not linearly separable. Right? The problem is, of course, that even these true labels we'll never observe. Right? So you can imagine these three classes, or all these dots correspond to patients. Right? In order to observe the true labels, we would have to do very invasive tests. What we do instead, we ask doctors and aggregate the annotations. So just as an illustration here, this is the true posterior distribution that we get. And you can imagine the ambiguous example on CIFAR 10 I showed before is somewhere in between here, right? Where kind of there is an overlap between the blue and the red class, meaning there is some uncertainty, and annotators likely disagree if we assume that the annotators somehow sample from the true posterior. But there, of course, in CIFAR 10, most of the examples are very easy examples. So they might be more here on the right, where you look at the image and most annotators or all annotators agree that this is indeed an airplane. In practice, of course, we also don't observe the true posterior. So this is just for illustration purposes. What we observe, or what we usually get if we, for example, download the data set, or if we kind of aggregate labels from expert annotations, is this very simplified problem, which corresponds to our voting distribution, right? So if I were to ask annotators, and I assume these annotators sample their opinions from the true posterior, and I take the majority vote, then I make this problem by construction linearly separable, right? So again, here it's very clear that kind of this voting distribution for many of these difficult cases in the overlap is actually an oversimplification of the problem. Okay, so far for a toy example, let me actually try to convince you that this is a serious problem in many practical and safety critical applications. So here we have the problem of skin condition classification for images. So a patient can kind of take one or multiple images with kind of a consumer grade camera, so your phone, of your hand or whatever skin you feel is irritated or you feel you would go to a doctor for. And we want to know what is the underlying condition and make a recommendation in terms of a treatment based on this. Now, the problem is I'm not a dermatologist, so I can say nothing. But of course, we were smart and we asked several dermatologists basically to give us the differential diagnosis, right? So in health, instead of providing individual labels, many of these doctors are used to providing differential diagnosis. So you will see for each of these raters, you'll see that we get a ranking or a partial ranking, right? So they basically tell us, okay, condition A, I think is the most likely condition, but it could also be condition B and C with lower probability. You already see that there is quite some disagreement, just by the way. So in the parentheses, in the colored, you see that these risks have some structure, so they are lower and medium and higher risk conditions. But even by conditions, you see that these raters disagree quite a bit. You can see, for example, hemangioma is present in most of the raters, but not all. We also have melanoma, which is a skin cancer type, which is present in some of the raters. Now, of course, in this problem, it's even harder to come up with a majority vote, but people have thought about this and came up with different strategies. And if we apply one of them, for example, then the majority voted condition would be hemangioma. Hemangioma is a medium risk condition, but it's not a cancerous condition, right? So it's a benign condition. Now, the problem is working with this majority voted label, again, ignores very rich information that we have from the raters. More importantly, it totally ignores the fact that 4 out of the 6 raters actually said it could be melanoma, which is a cancerous type, right? So as a patient, I would assume that if my doctor has at least a small probability that it could be cancer, then we should at least kind of test it. So this is just to give you an illustration that there is actually severe impact if we kind of ignore this type of uncertainty. And the goal of this talk, or also of Monte Carlo conformal prediction, is essentially how can we embrace or use this ambiguity and this uncertainty during calibration. And ideally, of course, we would like to use these annotations directly. Instead of aggregating and majority voting, we want to use the rich information we have in the annotations. For example, we could use them more efficiently by operating on top of these aggregated annotations. For example, the frequency histogram for CIFAR 10, or also for the skin condition classification task, we can aggregate and assign kind of a plausibility, how plausible a specific condition is to be the ground truth label to the different conditions. And we did this also based on related work. And you again can see that there is actually a very close tie between hemangioma and melanoma, which is very plausible from the annotations you saw. And we call kind of these approximations of hopefully our true posterior the aggregated distribution PX, just to make it a bit clearer. Of course, ideally, we assume that if we have infinitely many raters, then our aggregated distribution would converge to the true posterior, right? In practice, of course, in the finite data regime, this will not be the case. So you could argue why actually kind of do this if we cannot guarantee anything with respect to the true distribution. And the main point here is, or my argument is, that kind of aggregating annotations and calibrating or training against what annotators believe is the best we can do, right? This basically assumes that if I ask experienced dermatologists what this condition is, then neither me nor my machine learning model should be able to perform better than these dermatologists, right? Especially on cases where dermatologists disagree a lot. Of course, this is subject to kind of the ratings and the quality of the raters and so on. But given the data we have and the raters the annotations we gathered, then our goal should be to be as good as the expert annotators. So now the next question is, how can we calibrate against these aggregated distributions of labels rather than majority voted labels? So for this, the first thing we need to figure out is how do we define coverage in kind of this space where we don't have a one unique majority voted label, but we actually have a distribution over labels. And just to simplify notation a bit, I'll call this aggregated distribution lambda, and I'll refer to them as plausibilities, with the main idea that these are, of course, the relationship between PX and the true distribution is a bit difficult, but basically we assume that these annotators, after aggregating, give us an indication of how plausible the specific label is to be the actual ground truth label without ever observing the ground truth label. So that's where the term plausibilities comes from. So now on this CIFAR 10 example, we can write down lambda as a vector. So you can see 32% said it's a bird, 46% said it's a cat, and so on. So now if we have a confidence set and we want to evaluate coverage, what we typically do, we look at the majority voted label, we see is the majority voted label part of the set, and then we say, yeah, if that's the case, then we have coverage, right? And in this case, the majority voted label as before is cat, it's included in the set, so we have coverage. The problem is, of course, that we ignore quite a bit of the plausibility mass, right? We ignore many, many annotators. So a more realistic statement would be what we call aggregated coverage, is basically look how much of our plausibility mass is covered by the prediction set, by the confidence set. So in this case, we have cat, which is 46% of the annotators, and dog, which is 16% of the annotators. So our aggregated coverage would be 62%, right? So you can imagine this is kind of the plausibility mass that we cover. And you also see that instead of having a binary event, right, in the majority voted case, we either the majority voted label is in there or not. So it's kind of a 0-1 thing. Aggregated coverage is actually a value in between 0 and 1. So it's a bit more differentiated. Okay, so how can we generalize this to kind of more test examples? So what we are interested in here is evaluating basically coverage, so the likelihood that the true label is included in the true confidence set C under this kind of aggregated distribution of our plausibilities. And this can be understood as essentially guaranteeing coverage against the annotators. And if we write this down, because the event is a binary event, we can rewrite this as an expectation over our distribution, and we can further kind of decompose this distribution as our test example sampled from the true distribution, and then our labels being sampled from this kind of aggregated distribution to which we have this proxy through the annotators. All right, so now if we split this kind of expectation up as usual, we see that the outer part is as we would implement regular kind of coverage, we would take a sum over our test examples. This is kind of the expectation on the outside. But then we have this expectation, this inner expectation here, which is kind of new, because before we only had one label per test example, but now we have kind of this distribution, these plausibilities. So this essentially boils down to having kind of an expectation over these plausibilities, which means that for each test example, we look how much of the plausibility mass is covered. And the interesting part here is that you can see that previously, if the inner part is a binary event, then coverage, so conformal prediction, essentially decides for which examples do I have coverage and for which examples don't I have coverage. In this case, it's slightly different because on top of this decision, the calibration algorithm can now also decide how much coverage, how much of the plausibility mass do I want to cover for a specific example. Okay, so yeah, this is basically just what I said. So coverage is now marginal over both the examples, so the probability is taken over both the test examples, as well as kind of the labels, which follow this kind of aggregated distribution according to my plausibilities. So now note that if we can perfectly approximate the true posterior distribution by asking basically infinitely many raters, then this coverage is actually coverage with respect to the true labels, right? So if we have full knowledge, then this is the coverage we want to have, acknowledging that our posterior distributions of labels y given inputs x might be ambiguous. So there might not be one hot, there might be multiple labels given the limited observational information which are plausible. So on the toy example, just to give you an impression of what happens in practice, on the toy example, we of course have full information, meaning we have the true labels, we can compute coverage against the true labels, and we can use the true posteriors as our plausibilities. All right, so on the left, just to reiterate, these are our plausibilities in a sense, our true posteriors. On the right, we have our voted labels. And now what we do is we perform standard conformal calibration with respect to the voted labels. If we calibrate against the voted labels, then we obtain a coverage guarantee on the voted labels. So we calibrate here for 95% as indicated in red. And you can see that on average, so here the histogram is over random test and calibration splits. On average, we see that we get actually 95% coverage against the voted labels, right? This is clear because this is standard conformal prediction. The labels we calibrate against, we also get a guarantee against. Now, the problem is as soon as we evaluate coverage with respect to the true labels, which in this case we have access to, in any practical case we usually don't, coverage is actually significantly lower, right? So you can imagine for many of these examples in between blue and red here, right, where we oversimplified the problem, we don't cover the true label because in our calibration set, we never actually observe anything close to the true label. And you can see that this gap here is quite significant. Of course, the gap depends on how much overlap I have. If I move the Gaussians closer together, the gap will be larger. If I make the problem perfectly linearly separable, the gap will be 0. Okay, but this is kind of the gap we observe, and the assumption is now that on our skin condition classification case, for example, we will have a similarly severe gap, and this gap will of course directly translate to kind of making mistakes for many patients. Okay, so now how can we calibrate against these plausibilities instead of majority voted labels? And here the basic idea is really we want to use the plausibilities by sampling labels from them at calibration time. So the simple procedure here is we repeat each calibration example we have m times, where m can be kind of any number you want, could be 1, could be 10. And then we kind of repeat these examples, and for each repetition, we sample a new label, right? So our new calibration set, we basically create an augmented calibration set, looks like this. We have the repeated observations, they don't change. And then for each repeated observation, we sample a new label according to the plausibilities. Now we can imagine on very easy cases where there is a clear label that all annotators agree on, these labels will always be the same. But on the examples I showed before on CIFAR 10 or in the skin condition classification case, I might sample different labels, of course, in the limit proportional to kind of the plausibility. So now this is kind of a perfectly fine strategy. The main problem with that is that if we now apply standard conformal prediction, we won't get a coverage guarantee. And the main reason for this is because this augmented calibration set invalidate or breaks exchangeability, right? So just as a short side note here, what does exchangeability mean? Exchangeability is usually tested by looking at the joint distribution of my calibration example. So these are my calibration example Zij, where I have basically each original calibration example Zi repeated m times, right? And then I have the test example Z for which I want to have my coverage guarantee, which is of course, and in the conformal framework, this is of course all assumed random. And in order to have exchangeability, I basically need this joint distribution to stay the same, to be invariant to any permutation, right? So we can very easily check this. Let's assume we take the test example Z and we swap it with the first calibration example, Z11. Now the problem is the distribution clearly changes because I know that the first m examples will be the same, and suddenly they are not anymore, right? So it's a very simple argument why exchangeability is broken. If exchangeability is broken, then we also don't have a coverage guarantee. So the question is, how can we fix this? And it turns out that we can fix this fairly easily on the surface by just adjusting the quantile computation, right? So if we remember before, we had this calibration set, we compute these conformity scores, and then we compute roughly the alpha quantile. And the only thing we need to do here is to adjust this alpha quantile computation slightly by taking into account the number of repetitions m, right? You can very easily see that if my n is very large, especially if my n is significantly larger than m, then both will roughly be an alpha quantile. So in practice, actually not a lot of things change, but we need this change in order to have a coverage guarantee. And this is also the point where this alternative p-value formulation comes into play, because there are essentially two ways you can show why this alpha quantile this quantile change is necessary in order to get a coverage guarantee. And the more intuitive one, at least for the presentation, I believe, is to go through the p-values. So let's do a small exercise and look at the p-values of this problem. So consider that we have the p-values and we compute them using standard conformal prediction. So remember that for the p-values, you basically look at the conformity scores on the calibration set. This is the first term here. And we compare them to our test conformity score. And we just count how many of our calibration set or how many conformity scores on our calibration set are smaller or equal to our test conformity score. We have this +1 correction factor. And then we divide by the number of calibration examples. Now, of course, the number of calibration examples is m times n plus 1, right? And so you see that the only thing that changes is that we have this factor m here, and we, of course, have this additional sum over m. So the problem is, of course, that these +1s are a bit annoying. So let's get rid of the +1s for a second. So if we get rid of the +1s, what we can do is we can basically move this kind of sum over these m repetitions. We can move it outside along with the 1 over n, which means we can rewrite this as kind of an average for each example. For each repetition, essentially, we compute a p-value. This is rho kj. And then the overall p-value is basically defined as the average, right? So this is just moving the m and the sum outside while ignoring the +1s. So now if I look at this kind of in a p-value, I rewrite this, the only thing that's left over is of course the sum over n, the comparison, and then the n in the denominator. And the problem is that you'll realize that this is not a valid p-value, right? So for large n's, in practice, it will look like a valid p-value and kind of the mechanism will usually work. But in theory, you can show that this p-value is not uniformly distributed anymore, which means that it's not kind of a valid p-value. So if you construct your confidence sets using it, you don't get a coverage guarantee. So now we can reverse engineer the thing. So we can ask, okay, I want this to be a valid p-value. In order to achieve this, I just need to re-add these +1s here, right? So now I change this. So I want this p-value to be a valid p-value, and I want to kind of follow this idea of averaging p-values. So the question is, how do I need to adjust the original p-value in order kind of to account for this? And it turns out that the main thing that changes here is that kind of the denominator changes slightly from m times n plus 1 to m times, in parentheses, n plus 1. Right? So I hope that this is kind of a fairly intuitive way of illustrating it. But now the main point here is that we kind of reformulated the p-values we get from Monte Carlo conformal prediction as averaging p-values. And for averaging p-values, there's a very established literature that tells us that if we average a p-value independent of whether these are dependent or independent p-values, in this case, of course, these p-values are usually highly dependent, we can get a coverage guarantee of 1 minus 2 alpha. So we get, so by doing this averaging, we kind of lose a bit of coverage in theory, which is kind of this factor 2 here. Okay, so overall, Monte Carlo conformal prediction can be reformulated as averaging m p-values. As I said before, you can do the same exercise essentially on the quantile. It's just kind of a bit more of arithmetic work, and I think it's a bit less intuitive. And this then establishes a coverage guarantee 1 minus 2 alpha. Now you might say, of course, the 1 minus 2 alpha is not what we want to have. We want to have 1 minus alpha. So in the paper, we show that this can actually be improved arbitrarily closely to 1 minus alpha by obtaining a coverage guarantee of 1 minus alpha times 1 minus delta for any arbitrary user-chosen delta, if we are willing to spend some data on it. So essentially, if you have enough calibration data and you are willing to have an additional calibration split, then you can kind of get arbitrarily close to 1 minus alpha. So now the good news is that in practice, you usually don't need or don't want to do this, because the observed coverage, the empirical coverage we observe when running this algorithm, is usually 1 minus alpha. And actually, you don't have to believe me. There's actually quite a bit of literature on this phenomenon, because it's very similar to, for example, cross-validation conformal prediction, or in general, conformal prediction approaches that are based on bagging or bootstrapping ideas. In all of these variants, the theory only establishes a 1 minus 2 alpha coverage guarantee, but in practice, we almost always observe 1 minus alpha. And I really sat down a couple of weeks and tried to kind of break this and try to find example that where you deviate from this 1 minus alpha, and I really couldn't. So another important remark is that if there's no ambiguity in the data, meaning all annotators perfectly agree, my true posteriors are always one hot, then Monte Carlo conformal prediction basically recovers standard conformal prediction, right? Subject to kind of the discussion above. But the results are essentially identical. The confidence sets you get are the same. More importantly, even, because usually we don't have either a super ambiguous task or a super clear-cut task, usually in each data set we have ambiguous examples and less ambiguous examples. And the nice thing is that on these ambiguous examples, Monte Carlo conformal prediction improves things, improves coverage and guarantees coverage, while on the unambiguous examples, it just kind of falls back to standard conformal prediction, right? So if you have a fixed data set and you swap from standard conformal prediction to our Monte Carlo conformal prediction, then on the ambiguous examples, you will see a bit of difference. On the unambiguous examples, you will usually not see a difference. Of course, the calibration might redistribute your coverage slightly different, depending on randomness, but the prediction sets are usually very similar. Okay, so finally, some results on the dermatology case study. So here I basically repeat the same experiment as I did on the toy example before. We do standard conformal prediction by calibrating against the majority voted labels. And we evaluate against the majority voted labels in blue, right? So we calibrate for 72% coverage. You can see that on average across random test and calibration splits, we also get 72% coverage against the voted labels. But we have severe undercoverage if we now evaluate aggregated coverage, right? So the key difference between the synthetic toy example is that here we don't observe the true labels. So we assume that the plausibilities is the best information we have. We compute aggregated coverage against the against these plausibilities, and you can see that there is severe undercoverage, so at least 10% lower coverage than what we would expect, right? So now with Monte Carlo conformal prediction, we can fix this. You can see that now our aggregated coverage is on average 72%. It's actually not 72, it's roughly 72.6 because we calibrated for a baseline model from related work. But you can see that our coverage target is kind of achieved on average. Of course, the gap between aggregated and voted coverage stays the same. So against the majority voted labels, we now have significantly better coverage. And on the bottom, you can see the histogram of the average confidence set sizes, so the inefficiency. You can see on the left, this is 2.6, and on the right, this is roughly 4.6. So you can imagine that this increase in the average confidence set size is essentially the cost you have to pay in order to handle these ambiguous examples correctly. And on this particular data sets, there are at least half of the examples are usually considered ambiguous. So you can that's why this kind of increase by roughly 2 classes per confidence set is quite significant. And just to convince you that this has actually a real impact on kind of patient outcomes, here is our my running example from before, where standard conformal prediction basically covers the voted label. So hemangioma is the top one voted label. This is covered. So in blue, we again have the plausibilities. In green, we have what is included in the confidence set. You can see that the plausibility mass we cover is only 41% roughly. And now with Monte Carlo conformal prediction, we cover a few more conditions. Most importantly, we cover melanoma, which is kind of the high-risk condition that is very plausible, mostly like nearly equally plausible than hemangioma. And this is, of course, something we want to test for. On the bottom is an even more ambiguous case. Here we have 5 classes. Annotators seem to agree that much that these 5 classes are more or less equally plausible. Standard conformal prediction covers 2 of them. With Monte Carlo conformal prediction, we cover 3. Of course, Monte Carlo conformal prediction will not kind of solve everything, but it takes into account these plausibilities, and depending on the alpha you choose, you might get more and more coverage. Okay. Yeah, just as a conclusion, so we have some time left for questions. Monte Carlo conformal prediction is essentially conformal prediction with labels, with ground truth labels, calibration labels, sampled from annotators or plausibilities. So you can imagine you can apply this procedure either directly to the annotators. So on CIFAR 10, you could do this, for example. On the skin condition classification task, this is harder because the annotations have richer structure because we have these kind of rankings. And in these cases, we might want to aggregate these rankings in a reasonable way to get the plausibilities. And the main story of our work is essentially realizing that calibrating against the voted labels, what we usually do, is not sufficient in ambiguous setting, especially the health setting I showed. And by sampling labels from the plausibilities or directly using the annotations and calibrating against that, we can fix it. But we need to be a bit careful if we want to kind of preserve the coverage guarantee that conformal prediction provides. And the bottom line is essentially that calibrating with respect to the annotators is always kind of the best we can do. It kind of takes into account the uncertainty or the disagreement among annotators essentially very directly. And the nice thing is it scales with your data. So if you have more annotations, then the Monte Carlo conformal prediction will automatically adapt or get better. And as a side note, I didn't show experiments for that, but if somebody's interested, please ask me. The Monte Carlo conformal prediction is actually also the first method that establishes formal coverage guarantees for multi-label classification. In multi-label classification, there's a very similar approach that works well in practice, but so far hasn't been associated with a guarantee, which is that for each label in your multi-label set, you repeat the example and then you perform standard conformal prediction. So you can see that this is very similar to Monte Carlo conformal prediction, and we can actually show that we can get a coverage guarantee for that. And another variant of Monte Carlo conformal prediction also allows to take data augmentation into account. I mean, for evaluation, robust evaluation, and also for training, data augmentation is extremely common. For conformal prediction, people usually didn't do data augmentation because it changes, because it breaks exchangeability. And Monte Carlo conformal prediction basically provides the theory to use data augmentation for calibration as well. Okay, so here's the paper link, and as always, feel free. So of course we have time for questions, I hope. If not, feel free to reach out and ask questions via email or on social media.
Fantastic. Thank you so much, David, for the wonderful talk.
Yeah, thanks for having me. Any questions?
Questions, yeah.
Seems we have someone with their hand raised.
Yeah. Okay, you need to figure out how to.
Yeah, I can do that. I can let Kehan. Just a second.
Hi, David.
Hi.
Thank you very much for the great talk. So I have a question about the way that you aggregated the p-value.
Yeah.
So if I understand it correct me if I am not understanding correctly. I could have viewed this as so I can run the typical conformal prediction, except that this time the labels are coming from the sampling of your plausible distribution, and I can run it m times, m like gamma, and then I come up with the m different p-values, and somehow have to combine.
Yeah.
So one question that I have about this specific slide is that now I have m different p-values, and one way of combining these p-values is to compute the average. And the +1 is a way for correction. Is that the best we can do? Because there is a literature about like how to combine multiple p-values under different regimes of correlation. Is that the best that is achievable here?
Yeah, that's a very good question. This was essentially a couple of months of my last year that I spent going down this rabbit hole of combining p-values, where you're right that there is a very rich literature on it. So we tried. So there's not a lot of traces in the papers though. So feel free to follow up either now or via email. So there is of course a lot of literature on combining p-values. All the standard methods that we know, like Fisher's method and so on, usually assumes independent p-values, which is not the case. There are extensions for dependent p-values. Very often, then you have assumptions on the dependence, meaning you work with kind of correlation or covariance structures among your test statistics and so on. And these methods work well if you know the dependence, then you get your kind of the guarantees you want to have. If you don't know your dependence and you need to approximate your dependence, then of course your p-value are not immediately valid. They are only valid in an asymptotic sense, right? And the idea of like, if I have enough data, I can approximate my kind of correlation structure perfectly, and then my p-values. I know the dependence structure, and then I can apply like some variant of Fisher's or Brown's method and so on, and I get what I want to have. So there is a lot of literature on this. Then there is the work that I cite here by Wok and Wang, which is a very general thing, and that's why we also went with it, which basically gives you guarantees of combining p-values independent of the dependent structure. So they can be independent, they can be dependent, for various ways of aggregating them, right? So averaging, kind of taking the maximum, and so on and so forth. Which of course covers a lot of the standard methods as well, like Bonferroni's thing, which is kind of a maximum or minimum, however you will formulate it. So these are kind of the two things, and then the third one, which actually alludes a bit to what I mentioned here, how you can get better guarantee, is also a data-driven one, where you basically say, okay, I have my average p-value, so row bar here. And if I, of course, have enough data, then I can approximate the distribution of this average p-value rather well, right? So let me just for illustration, let me just pull over an illustration. So this is just an example. You can run in a Colab. If you have the independent p-values and you average them, then you will have something like the flu distribution. right? And if you can do this often enough, you can of course approximate the clue distribution, and you can apply kind of very simple concentration inequalities to correct for that, right? And
I guess you're sharing different page. But
oh, sorry, I'm sharing different. Oh yeah, sorry. I shared the window and not the screen. Can you see the paper now?
Yeah.
Okay. So just an illustration, and then I'll make it a bit shorter. So on the left, if we average 10 p-values and do this kind of 1,000 times, then the distribution of this average p-value is clue, and we can correct for that because if we know empirically this distribution, we can correct for it in a data-driven way. You can apply, because it's one-dimensional, right? You can apply very simple concentration inequalities that basically scales with the number of examples you have. This is then called like a ECDF, which is an empirical. So the correction is based on an empirical CDF, on an empirical cumulative distribution function. And this is kind of the second approach I mentioned here, where your delta basically comes from the concentration inequality that you use. So if you have enough data and you're willing to split your data, one for the actual conformal calibration and one for estimating this distribution, then you can do better. And so far, I'm not aware of any other way to do this better with dependent p-values where you don't know, or where you don't have an analytical form of your dependent structure.
There is a method called Cauchy method for combining p-values. I don't know if you heard about it. That does not assume any.
No, I haven't.
It does not assume any. So
yeah,
that basically may improve your delta, but that's later.
Okay.
Yeah.
Can you send me an email? I'm not sure if I remember the name, but that would be great. I mean, it's a bit of became a bit of a side hobby of mine to go through the literature. Because
thank you very much. It was a great talk.
Yeah. Thanks for the question.
Great. Yeah, so I may have missed this detail, David, but like the effect of M, like you said 10 at some point in your talk, but like can you comment on the effect of M, like how large it should be?
Yeah, that's a good question. And so maybe just to let me go to the general slide. So in general, of course, you like with M equals 1, so M equals 1 is enough to get the guarantee, right? So the sampling itself is enough. You don't necessarily need, with M equals 1, you also don't have an exchangeability issue, which means you kind of get coverage 1 minus alpha instead of 1 minus 2 alpha. The problem is, of course, there is a trade-off. So if I have M equals 1, then in my toy example, so if I have enough examples in my calibration data set that are kind of in this overlap here, then M equals 1 might be enough because I see enough examples that are very similar. And sometimes I sample the red label, sometimes the blue. So kind of the method can figure out the proportions essentially. In practice, of course, I very rarely observe a lot of ambiguous cases. In the health setting, for example, we have a long tail. So most of the cases will be fairly clear cut, right? In the skin conditioning example, a lot of cases with acne or similar rashes. And less examples are examples where you really have this combination that I showed before, where annotators disagree between like a cancerous and a non-cancerous skin type. So what I'm essentially trying to say is that if you have enough data, M equals 1 might be enough. In practice, if you don't have data, then you might want to take a higher M to leverage essentially the annotations you have. Because if you go to the annotations realm, M equals 1 means you only need 1 annotation per example. Right? In practice, of course, what you usually do is you get multiple annotations anyway, and you want to make the most use of these annotations. So M equals 1 would ignore most of these annotations. And just to give you an impression empirically, as I said, right, so if you do enough test calibration splits, on average, you will always get your target coverage. So this is on the toy data set that I showed before. The M basically just takes care of your spread, how lucky you can be, right? So, and this is, of course, most impactful if you have very few data. So here I have another plot where I have the fraction of calibration data. So I have a fixed data set. I think it was 10,000 examples, and I only use 10% of that or 5% of that for calibration. And you can see that this variation is, of course, the highest if I have less calibration data. And in these regimes, going with a higher M empirically reduces the variation, which means that at test time, right? So for production, where you need to fix your calibration set, you can't do these kind of calibration test split experiments, then it's more likely that you're actually performing well. So that's kind of the main impact. In some of these other applications, like multi-class classification, your M is fixed per example by the number of labels that you have. And in the data augmentation thing, it's again a trade-off. If you want to have a bit more robustness to some augmentations, then you want to have a higher M essentially. Yeah, I hope that was what
Yep,
you were
absolutely.
going for.
Yeah. Given that we are at the end of the time, any last questions?
I guess a quick question, just from a
Yep.
Empirical standpoint. I guess, are you familiar with any work that looks at pseudo labels as compared to these ground truth, like expert-driven labels, of how applicable this might be in those scenarios?
You mean pseudo labels in terms of like from the self-supervised sense, or from?
Yeah, something like that.
Yeah. I'm not aware of any literature on that, specifically for conformal prediction in these settings, right? I mean, if you have a self-supervised problem, of course, then that conformal prediction will give you the guarantee that you would expect, right? Like if you calibrate against self-supervised label, you get a guarantee against self-supervised label. So if you have self-supervised label, but you are interested in some other labels and you think that the self-supervised labels are a good proxy, then you have kind of the same problem that we have in the paper, that you somehow need to take into account what the difference between these two distributions is, right?
Different experts.
In general, of course, so one thing, so I think Arno, one of my co-authors, actually in the paper actually calls it conformal prediction with pseudo labels, our Monte Carlo conformal prediction. So I think the thinking is similar, but depends a bit on what application. Maybe you have something specific in mind, then I can elaborate a bit more, but otherwise.
Yeah, I'll probably reach out then.
Yeah, sure.
Thanks.
Fantastic. Yeah, thank you again, David. This was a fantastic talk. We really appreciate your time. And yeah, we'll be in touch. I hope that we will send you emails and follow up with other questions that we may have.
Yeah, please do. I'm very curious. And thanks again for having me. It was very nice as last time.
Thank you.
Perfect.
Have a good day. Bye.
Yeah. Have a nice day. Bye.
Thank you.
Yeah, thanks.